Okay, so now that we know how to obtain the equivalent capacitance for circuits where the capacitors are in series or in parallel, let's try to solve a problem. Okay, well, let's just write down first what we learned. So if the capacitors are in parallel, we know that we just have to sum the capacitance, right? So that will give us the equivalent capacitance just by summing them. If there are 2, 3, or 4, I just sum. If the capacitors are in series, then we have to play with this 1 over the equivalent capacitance will be 1 over C1 plus 1 over C2. Okay, let's keep this there and let's see what the problems are asking. Let's start with this problem on the top. This problem is a symbolic problem. You see there are no numbers. Okay, this is the circuit. And you see that we have two capacitors that are in parallel, and then another capacitor there is in series with them. All right, and we want to find what is the equivalent capacitance of this whole circuit. Now, so determine the capacitance of a single capacitor, that's the equivalent capacitor, that will have the same effect as this whole combination where I have C1, C2, and C3. Okay, so in other words, let's try to keep that same battery and find what is the equivalent capacitor. Okay, so remember the battery has two lines. One is larger than the other one, where the potential is larger, while the capacitor, the two lines have the same size. Okay, so what is this equivalent capacitance? Well, when I see a circle like this, the first step is to get rid of this piece here where the capacitors are in parallel. Okay, and so what is the equivalent capacitance for this piece here? Well, the equivalent capacitance for this piece here, which is what the book is calling C23, so the equivalent capacitance for that piece, what the book is calling C23, is just the sum of C2 plus C3. Now, if you read the problem, they tell us that C1, C2, and C3, they all equal and given by a certain letter C. That's the symbol. So that means that the equivalent capacitance for that parallel part of the circuit is just 2C. Okay, so we simplified, that was the first step. Now we simplified this circuit here. So let me write this again. Our original circuit is battery, C2, C3 in parallel, so C2, C3, and then C1 in series. Okay, so our first step was to simplify this piece here, to substitute this piece. So now we have battery. Instead of that piece, now we have the equivalent capacitance for that piece, which is this 2C that we obtained. Okay, and then we have the other capacitor, the C1, which is also C. Okay, and then the battery. Okay, now I can go one more step and now get rid of this remaining part. Now what we have here, two capacitors that are in series, and now I know that the equivalent capacitance here, which is it's going to be the final equivalent capacitance, is going to be 1 over 2C plus 1 over C. Okay, well, common denominator is 2C, so I have 1 plus 2, which then means that the equivalent capacitance is 2C divided by 3. That's the answer of the problem, and that's what you're seeing here. All right? Okay, so we are done with this part of the problem, which was a symbolic problem. Now we're going to use that same circuit, this circuit here, the same circuit, but with numbers. Okay, so let's write this circuit again. What we have, the battery, and the battery, they are giving us the value, now the number, the potential difference is 4 volts. Okay, then we'll have first those two capacitors in parallel. Each one has 3 microfarad. that's the capacitance of each one. And then the other one, the C1, also has that same capacitance, 3 microfarad. Okay, so this one on top is the C2, this one on bottom is the C3. That's the problem now with numbers. And then the question is, determine the charge on each capacitor. So we want to find Q1, Q2, and Q3. And we want also to find the voltage across each one. So V1, V2, and V3. So let's write down what we want. We want to find Q1, Q2, and Q3. Okay, and we want to find V1, V2, and V3. Okay, before we do anything, we have to find what is the Q that is being drawn from the battery. And that we can do because we know what is the equivalent capacitance. We found it. Okay, so the equivalent capacitance of this whole circuit is 2 multiplied by C. So is what we have here, 2 multiplied by C divided by 3. So that means 2 multiplied by 3 microfarad divided by 3, which means the equivalent capacitance of this whole circuit is 2 microfarad. Okay. With that, we can find what is the total charge that is drawn from this battery. How? This total Q is equivalent capacitance V, which means equivalent capacitance is 2 microfarad. Let me keep the units here, microfarad. And potential difference, the potential difference is 4. Okay, so this means that we're multiplying 2 10 to minus 6 Faraday by 4 volts. This means that the total charge is 8 10 to minus 6, so 8 microcoulomb. Okay. This is the charge for the whole circuit. So this is the Q that is being drawn from the battery. Once it reaches this point where we have these two, C2 and C3, this Q will split and will split equally. So we can say that Q2 and Q3 are equal and they are half of this whole charge that is being drawn from the battery. Okay, so we found that Q2 is then 4 microcoulomb and Q3 is also 4 microcoulomb. This answer is not here on this slide. Okay, so this is missing. Okay, here on the slide we just wrote the Q for the whole circuit. How about Q1? What is the charge for Q1? Well, the charge was drawn from the battery, split into these two capacitors, but at this point they get together. And so we have again the whole charge from the circuit. So at Q1 we have the whole thing, we have 8 microcoulomb. Okay? All right, so we are done with the charges. Now we want to obtain the potential difference of each one of these capacitors. Let's start with V1. Well, what is the equation that we need here? We know that Q is CV. So we know that V is Q divided by C. Okay, so if I want to find the potential difference across the capacitance 1, what do I need? The charge of that capacitor, and the charge we saw is 8 microcoulomb, divided by the capacitance, which is 3 microfarad, right? So what is going to be the potential difference across the capacitance, the capacitor 1? 8 divided by 3. Now we have both are micro, so both are 10 to minus 6. So 8 divided by 3 8 divided by 3. If you compute, you will see that we get 2.7 volts. Okay? All right. This is what we have for the capacitor 1. How can we get the potential difference for the other two capacitors, C2 and C3? There are two ways that we can do that. One is just by remembering that the potential difference of the battery is going to be equal to the potential difference at this piece, this VA, let me call this VA, minus this point here, VB, okay, and plus this potential difference VB and VC. Okay, so in other words, the potential difference of the battery is the sum of that piece that is in parallel plus V1. So this is one way that will give us the potential difference for the piece that is in parallel. We know that the potential difference for C2 and the potential difference for C3 is the same because they are in parallel. So one way to get this value is by using this sum. Another way, maybe easier for you, is again just to use this equation here. What is the potential difference for the capacitor C2? Well, I can just use this equation, which is the charge Q2 divided by C2. What is the potential difference for the capacitor 3? Well, the charge Q3 divided by C3. These two are equal because they both have the same charge, they both have the same capacitance. What is the value that you're going to get? Q2, we just said, is 4 microcoulomb divided by C2, which is 3 microfarad. So again, I repeat, micro is 10 to minus 6, micro here is 10 to minus 6, so we are just dividing coulomb by Faraday, we'll get volts. 4 divided by 3 will give us 1.3 volts. Same thing here for V3. 4 microcoulomb divided by 3 microfarad will give us 1.3. Okay, so you have two ways to obtain the potential difference for this piece here, okay, this piece here, this piece here, for the parallel part of our circuit. There are two ways, either by using this equation where the potential difference is the sum of the potential difference of each piece of the circuit, or by using this equation here, potential difference is Q divided by C. We have Q, we have C, so it's straightforward to obtain these values. Okay, so this is the end of these problems.